So with that, it is my pleasure to introduce our speaker for today, Dr. Thomas Maccarone, who is a Presidential Research Excellence Professor at the Department of Physics and Astronomy at Texas Tech University in Lubbock, Texas. Professor Maccarone will be talking today about the sharpest view of neutron stars and black holes. Without further ado, I turn the control over to Professor Maccarone.
Okay, thank you, Laura, and thank you to the NRAO staff for organizing these events. I'm going to talk about an ultra-sharp view of compact objects, and I'm going to talk about a variety of results and things that we might hope would become results with the next generation VLA. And so I'm going to flash the names of all of the people who've helped contribute to these ideas here at the beginning, but I'm not going to read them off because I don't want to use up too much time on that. All right, so just to give you an overview of what I'm going to talk about. So I'm going to talk a bit about the next generation VLA itself, since this is the first talk in the series. And I know not everybody is familiar with the capabilities and why this is such an exciting opportunity for us. So the tagline for the project is thermal imaging on millisecond scales, but I'm actually going to mostly talk about non-thermal cases, because it turns out that for certain classes of objects, especially accreting black holes, which have flat radio spectra, they tend to be observed best with the same kind of facilities that you use to look at, to do thermal imaging of cold objects. So I'll talk about finding black holes to build up population statistics and to understand those sources better. I'll talk about astrometry of stellar mass and supermassive black holes, and then I'll talk a little bit at the end about jet physics that we might do with the next generation VLA, and some ties to system parameters that come from the approach to jet physics I'll talk about at the end. Okay, so first of all, I want to just give you an idea of why the next generation VLA will be so much more sensitive than everything else that we've had to work with in the past. So the existing facilities that we have that are the best in the world right now are ALMA, which is the blue curve, and the current very large array, which is the red curve here. The mostly European project to move things forward, although it will be in South Africa and Australia, and they're both major participants as well, is the square kilometer array. And this is illustrated in purple here. And then the pink curve here is showing us what the next generation very large array will be. And the y-axis here is effective area divided by system temperature. And so that's a better metric than raw effective area for how sensitive a facility will be. And you can see that we're several times more sensitive than the square kilometer array and cover a much wider range of observing frequencies and about an order of magnitude more sensitive than the existing facility. So this will really be a revolution in sensitivity if the next generation VLA goes forward. Okay, the other thing it'll be a revolution for will be spatial resolution. So you can see here the next generation very large array, because it has a separation of the furthest apart antennas of about 10,000 kilometers, so almost the maximum that you can get on the globe. You can see that it'll have angular resolution that at its highest frequencies gets down to 1/10 of a milliarcsecond, and nothing else comes close that also has high sensitivity. So you can see in the radio band here, you tend to do very well by having very long baselines. And then as you move up to the optical and infrared bands, you can get away with having much shorter baselines because your wavelength of light is much shorter, but nobody has the really long baselines that we can do in the radio, and so the resolution isn't as good. And one thing I want to point out is that the best optical interferometer right now, Chara, has an angular resolution that's very similar to the NGVLA, and it actually has very similar sensitivity for things like stars as well. So these would be very complementary for studies of stars, and I'm not going to talk about that, but that's a very exciting possibility that's out there. All right, so now I want to tell you a little bit about the power of long baseline radio interferometry and why it's such an important technique. And the key here is that we have a very large fractional bandwidth that's possible, so you can observe a delta F over F that's almost 1 in the radio band, and you can still have the capability of recording or transmitting those data and the capability of analyzing them on a computer. And this allows you to put a large number of antennas at different locations and still be able to work with the data. Optical and infrared interferometry, in principle, if they could get the same baselines that we get in the radio, they'd be down at nanoarcsecond angular resolution, and they'd be able to do really fundamentally unique things. But the problem is that you actually have to interfere the beams of light. We don't know how to record or correlate data at bandwidths in the optical and infrared bands that are high enough to be able to get good sensitivity in those bands. So we're stuck with techniques that involve actually interfering the light. All right, so now a lot of what I'm going to talk about today is going to be related to X-ray binaries. And I just wanted to show a couple of images of X-ray binaries from Rob Hines' visualization tool, BinSim. And if you want to make these images, you can go to Rob Hines' website at LSU and download some software to do this. So on the left, I have GRO J1655-40, and this is kind of a canonical low mass X-ray binary. And by low mass, what we mean is that the donor star has a low mass, and it fills its Roche lobe, so it just gently spills material onto the accretion disk of its black hole companion that spirals in, gives off X-rays, and it sends out a jet at relativistic speeds that gives off the radio emission. On the right, there's an impression of Cygnus X1. This is what we call a high mass X-ray binary. This system has a very high mass donor star, about 80 solar masses, and it has a very strong stellar wind for the donor star. And that stellar wind, some of it is captured by an accretion disk. So you end up getting a much smaller accretion disk, and you still get this jet of material coming out. So if we're observing these things in the radio, we tend to be observing this jet, and we tend to be observing kind of in the upper part of the jet. If we're observing the X-rays, we're observing this accretion disk. If we're observing the optical, we tend to observing mostly the donor star, but sometimes some of the accretion disk as well. All right, so now I want to talk about one of the key problems here, which is the black hole mass distribution, and then also some of the other system parameters for the black holes. And one of the reasons this is so exciting is that if we're trying to understand how supernova explosions actually work, we can't do that by studying the supernova themselves. The supernova themselves have an optically thick envelope that's expanding. And by looking at the supernova, you can understand how much mass is in that envelope and how much energy was injected into it. But understanding the details of how that explosion actually took place is something that you can't do. And that can, in some cases, be done with gravitational waves or neutrinos, but those are very hard techniques to use. And probably even with future facilities, we'll get a number of objects that you can do something with that you can count on your fingers. But with stellar mass black holes, we know that there are probably about 100 million of those in the Milky Way galaxy, and probably around 10,000 of those are in binary systems of some kind where we could go and really understand them carefully. Right now, we know about 20 of these objects. So to really get a good understanding, we need bigger samples. Now, to give an illustration of something that you might be able to do to understand supernovae, if you have a really good sample of black hole and neutron stars, I show you this Belchinski et al. 2011 plot. And this is based on work that was done by Farial Özal and Will Farr in understanding what the mass distributions of these things really look like. So what you see is the black holes follow this kind of mass distribution here, at least the ones we know. And then the neutron stars are all in a fairly narrow mass distribution that's much lower. And there doesn't seem to be anything in the middle. Now, earlier this week, there was a report or something in this middle range from LIGO. And it'll be interesting to see if the gravitational wave observations end up filling this gap up. But in the meantime, we can also start trying to think about electromagnetic techniques for filling in this gap or showing that it's really there. And some things that you can't do with the gravitational wave observations are to understand, for example, what the natal kicks are for these systems. So in the supernova explosion, there's probably some asymmetry, and that asymmetry can cause the black hole or neutron star that gets produced to be ejected with a very high speed. In some cases, for neutron stars, this can be of order 1,000 kilometers per second, and a few hundred is very typical. So some of the things that we might like to understand with big samples would be to understand if there's a correlation between the masses of black holes and their kicks, and also to see if there's a correlation between the spins of black holes and their masses. And the electromagnetic work complements LIGO very well for this kind of study. All right, so now let's talk about how to find more black holes. So one of the important results from studies of X-ray binary jets is that there's this relation where most black hole X-ray binaries fall in this correlation, where the radio luminosity goes as the X-ray luminosity to the 0.7 power. So what that means is you get fainter and fainter, which is where most of the accreting black holes spend most of their time. You end up doing better and better with radio surveys than with X-ray surveys. And this is going to be especially true if we can get much bigger radio surveys that cover more of the sky and go much deeper. And we may even be able to, as this figure shows, observe some nearby galaxies and find some of the brighter stellar mass black holes in the radio in them as well. All right, so a few hundred hours with the next generation VLA can quintuple the number of black holes that we know that have low mass donor stars, and it can open up fundamentally new parameter space for finding wide black hole X-ray binaries that have high mass donor stars. All right, now, the way that you go about finding them is you look for radio sources that have flat radio spectra, and that will give you a sample that includes the objects that we're interested in, but a bunch of other things. A big fraction of the other things are going to be faint active galactic nuclei. And this figure kind of illustrates how you might go about separating those objects out, which is by looking at the proper motions of the object. So what we've proposed, and something that our host Laura and I took the lead on, is to do a survey of the galactic plane with the next generation VLA, but to do it in multiple epochs so that you can look for the radio proper motions and really filter out the sources that aren't what you're interested in. All right. The other thing that you can hope to do is to get better system parameter estimates, especially the masses and the space velocities. And some of that will come from getting the distances better. So with the next generation very large array, there'll be a good hope to measure geometric parallax distances for a large number of the stellar mass black holes. And this has been something that's been done a little bit with existing stellar mass black hole samples. So for example, this is from a plot from a paper by Mark Reed that did the parallax distance for Cygnus X1. Recently, Picchiatri did this for a new source that was discovered by the MAXI satellite. And so we can go and we can get really precise geometric distances. Now, some of y'all might be thinking, why not just do this with something like Gaia? And one of the problems is that a lot of these systems are very deep in the galactic plane. And what that means is that they have very high extinctions, and missions like Gaia that rely on optical data don't do well with them. All right, so in the radio band, you don't have to worry about the extinction. And something else that you can do for probably only a handful of cases, and there's only one good example of it so far, which is again Cygnus X1, is astrometric wobble. So for Cygnus X1, and probably with I would say a handful to maybe 20 of these objects as we go forward with NGVLA, you can actually see the motion of the star in its binary orbit. And in some of the best cases, especially high mass donor stars that might have strong stellar winds, you might be able to measure the astrometric wobble for both the donor and the accretor. All right, now, and so that's a nice segue into what I want to talk about now, which is that I think NGVLA should open up a new class of black hole X-ray binaries for us. And these would be wide binaries with high mass donor stars. So what these equations here do is they kind of work out how we can get a relationship between the radioluminosity that we expect and the orbital period. And we find that the radioluminosity, there should be a minus sign in there that I forgot, sorry about that. But the radioluminosity should go something like orbital period to the -2 power. And as a result of that, if we take an object like Cygnus X1, which has about a 5.6 day orbital period, we move that apart to say 60 days orbital period, we would expect its radioluminosity to be about 100 times lower. Cygnus X1 is 20 millijanskis. That would push it down to 0.2 millijanskis, which is a flux level that makes it really hard to work with on long baselines with current facilities, but that would be quite easy with the NGVLA. And so we could look for astrometric wobble from a system like that. Now, a lot of time work has been focused on trying to do this in the optical band, and there's a nice paper by Todd Thompson on one black hole binary candidate that came out using this technique. But as you go to longer and longer orbital periods, especially with massive donor stars, this gets harder and harder because the wobble that you would trace in the optical would be the wobble of the heavy object rather than the wobble of the light object. So the optical techniques would be good for low mass donor star systems, but not for high mass donor star systems. All right, now I want to show also how an example, and this is work that's under review at Science, and so it will be under embargo assuming it gets accepted, and the initial referees reports were very positive, so I think it will. So please don't tweet anything about this result. You can discuss it with other scientific colleagues, but don't put it out in the mass media. So a refinement of the radio parallax for Cygnus X1 has been obtained recently. And this is work led by James Miller-Jones with a lot of contribution from Arash Bakramian. And what was found is that the distance is a little bit further than the initial radio parallax distance. And that was due to some effects of the stellar wind that hadn't been taken into account properly in the original work. And so the increased distance leads to an increased donor mass, and that leads to an increased black hole mass. And now this black hole is probably a little bit more than 20 solar masses. And so this makes it by far the most massive stellar mass black hole that we know of from electromagnetic data. This also brings the distance into agreement with the Gaia distance that was out there, but makes it more precise, and also solves some problems with discrepancies between the donor star properties from past work and from current work. All right, so now I also want to talk about another example of something we could do. This is a paper I submitted a few weeks ago, looking at the object 4D1957 plus 11. So this is one of the objects that probably is in that mass gap. We don't have a good mass estimate for this object, but there are a bunch of good indirect indicators that suggest it's in that mass gap. In this case, we have a good proper motion from Gaia. Based on various assumptions about where reasonable distance is, we get a fairly broad range of kick velocities we expect for the system, but in no case is it less than 100 kilometers per second, and most likely it's about 300 kilometers per second. And this is something that had been predicted by theory, that the lowest mass black holes probably form from a temporary neutron star phase and then grow a little bit in mass by fallback accretion. But I think this is the best example of this that we have to date. And again, if we can start harvesting more and more black holes for our samples by doing radio surveys, we can expect to find more and more systems like this and see if the trends hold up. All right, now the other thing is getting good distance estimates for the stellar mass black holes helps us understand their spins. And if we can also get the inclination angles by using astrometric wobble, that helps even more. And this is from a paper by Jack Steiner, where he shows that for a particular system, it has a wide range of reasonable distances and inclination angles. And depending on which one you pick, the inner radius of the accretion disk in units of gravitational radii can go from anywhere from about 2 to about 5. And this allows for a huge range in black hole spins. But if you can nail down the distance and the inclination angle, and even if you just nail down the distance, that often helps you get the inclination angle better. If you can nail down those parameters, then you can really get precise estimates of the black hole spin. The other thing that's interesting to do here is if you can get the inclination angles from multiple techniques, like in the radio and through the ellipsoidal modulations from the non-spherical donor star as it makes its orbit, you can see if those end up lining up so that the jet is coming out perpendicular to the binary orbital plane. If it's not, then it casts doubt on a lot of the different techniques for measuring the black hole spins, but it gives you different interesting information about binary stellar evolution. All right, so now I want to move on to supermassive black holes, and I think there's going to be another talk about the jets from supermassive black holes by Roger Blandford a little bit later in the series. So I'm going to talk about astrometry of supermassive black holes instead. So one of the things that we can look forward to in the next decade is LISA, the Laser Interferometric Space Antenna, which is going to be a thing that will give us kind of minute to hour timescale gravitational wave sources. And there's a couple of nice bits of work. This is from a paper by Kyle Kramer et al. From a few years ago. But there's also similar work in Dongming Jin's PhD thesis. And that shows us that this noise curve here is what you would expect for the Virgo cluster distance. And at the Virgo cluster distance, you'd actually expect to be able to see some double black hole binaries with orbital periods in the few minute range. And by using them, you can get standard siren distances to those galaxies that'll be accurate to about 1%. And this will give us our best technique possible, at least with current imagination, for deprojecting where galaxies are within clusters of galaxies. And if we can do that, that gives us the hardest dimension of phase space to measure for what those galaxies' orbits look like. It's pretty easy to get the position and to get the radial velocity. We can do that now. And using those, people do statistical estimates to understand what the gravitational mass distribution looks like in clusters of galaxies. But if we can add in the actual distance from the center of the cluster of galaxy along the line of sight, and we can add in the motion across the plane of the sky, then we get the full 6-dimensional phase space information. And probably most of these galaxies that have standard siren distances will also have reasonably bright active galactic nuclei. So if we can go and do those over a 5-year time baseline with very modest exposure times, we should be able to get 10 kilometer per second proper motions for these galaxies. All right, and putting this all together, then you'd have real test particles that trace out actual orbits around the clusters of galaxies rather than just having to do statistical studies. It probably won't work for more than a couple of clusters of galaxies, but even a couple is a big deal in this game. Much larger numbers of galaxies with proper motions could be studied with using than would have the double black holes. So you could do statistical work much better for a much larger number of galaxies. And you'd also be able to do things like morphology kinematics correlations. So there are spiral galaxies that tend to be on the outskirts of clusters of galaxies, but it would be interesting to see if they're on their first passage towards the centers of the clusters of the galaxies. And this all comes from, this and the next slide come from a science book chapter I wrote with Anthony Gonzalez. And that benefited a lot from some discussions with Matt Benequista All right. So the other thing that you can do is you can look at merging clusters of galaxies. This is an image of the Bullet cluster, and I use it because it's a nice image. It's not something, it's too far south to look at with the NGVLA, but I think it's still potentially a really interesting concept. But there are a few clusters like Abell 2034 that are merging clusters where they would be observable by the NGVLA. And the expectation is if these things are merging with speeds of about 2,000 kilometers per second, you'd expect 1 microarcsecond per year proper motions. And it turns out with NGVLA, over a roughly 10-year time baseline, you'd actually be able to measure the proper motions of AGN in those galaxies to that precision. And so this is actually a doable project. So right now, people just kind of have to guess at what the velocity component is along the plane of the sky. All right, so now I want to move on to my last topic. My last topic is going to take us away from astrometry, but it will still connect in with some of the system parameter stuff that I talked about at the beginning. And this is looking at the eclipses of jets of X-ray binaries. So for understanding normal stars, eclipsing binaries are probably the most powerful tool that we have, because by doing eclipse mapping of one star using another star, you can really understand basically everything that you want to. The problem with X-ray binaries is not very many of them eclipse. But a while ago, I came up with this idea that the jet will eclipse in pretty much every case. And it was just during the coronavirus isolation that I found the time to work all this stuff out. All right, so if we're an observer sitting here, we look at this star, and the star is going to block some part of the jet. And the question is just which part of the jet. And what I found is that typically it's going to be in the high frequency radio part of the spectrum. All right, now, one disadvantage of this technique is it's the counterjet that's moving away from us that's always going to be eclipsed. And so if the jet is moving at a very high speed, then Doppler deboosting of this jet will mean that the effects of the eclipse will be pretty weak. But if we have neutron star jets, they're probably not moving very fast, and we should be able to map them out using eclipses. All right, and one of the key things here is that the eclipse duration helps you understand things about the inclination angle of the binary, and that gives you a very unique handle on one of the hardest to measure parameters of these systems. All right, so here's some calculations I did for the source Aquila X1. If it's in kind of one of its bright states, it's a transient, but it has outbursts that are very frequent. And so on the left plot, I'm showing spectra of the jet at different orbital phases. So the black is when you're at kind of full eclipse, and the blue up at the top is when the star is not blocking any part of the jet. And you can see there's a roughly 10% decrease in the flux of the jet. And this happens at about 30 gigahertz radio frequency. So this is basically just perfect for NGVLA. And on the right-hand side, I'm showing light curves for the jet in different band passes. All right, now, we can probably do some of this stuff as a proof of concept with the current VLA, because some of the interesting objects like Aquila X1 are fairly bright if you catch them at the right time. But it will be really hard to take full advantage of the power of this technique with just the current VLA. And the reason is that the current VLA only has 27 antennas, and you can only break it up, I think, into 4 subarrays at a time at most. And so, and it also has limited coverage. So what that means is you're going to have to guess at where the eclipse is going to be in the spectrum, and then set up observations. And you're not going to be able to calibrate at the right time, so you're going to have to figure out how to chop back and forth. And so if you want to really see what the jet variability is doing at many different frequencies at the same time, you end up being highly restricted with what you can do with the current VLA, even if you have a source that's bright enough. Fortunately, with subarrays, which will be something that will be much better with the NGVLA than with the current VLA, partly because there's so many more antennas, you'd be able to look across the whole radio spectrum all at once. And the power of what you can do even with the current subarrays has been illustrated in particular by some work by Alex Teterenko, showing what you can do for kind of other types of radio variability from X-ray binary jets. But with the NGVLA, this will become much more powerful. All right, so just for some conclusions, I want to just say that the high sensitivity, high angular resolution, high frequency, and broad wavelength coverage of the NGVLA are all important for revolutionizing studies of compact objects. And this will lead us to advances in things like as diverse as supernova physics, jet physics, and dark matter physics. All right, so I'd be happy to take some questions now.
Thank you so much, Tom.
For me.
Thank you very much, Tom, for those very interesting ideas about what we can do with the NGVLA. We have a number of really great questions. In particular, people are wondering how we actually can find the potential kick velocities, the data you were discussing.
Okay, right. So the potential kick velocities come from knowing several things about the system. So you need to have a radial velocity for the system. You need to have a proper motion for the system. And then the one that's actually the hardest is you need to have a good distance for the system. And so Picciatri did the calculation that went into that plot there. And what Picci's code does is she considers the orbit of the system and assumes that the system probably formed in the galactic plane, and then traces it back to the galactic plane and then says, okay, what's the velocity at the galactic plane crossing? And if you don't have a good distance estimate for the source, that gets really messy. So that's part of why we can generally do the radial proper motions really well already with the VLBA, but we have very few parallax distances with the VLA, and that's where the NGVLA will really revolutionize that.
Is there a follow-up on that at all from Allison? Or Lindsay was actually wondering how the predictions you have compare with some lower kick predictions that have come from Mandel and Mueller 2020. Do you know about that paper?
Okay, so I think the kick velocities, you could probably get theoretical codes that'll predict whatever you want. And so I think that's why it's so important to go and measure it. And so you get some constraints on that just by the total LIGO merger rate. And if we start to get good, and for the neutron star systems, you can go and measure it in one case, and you can also see where the mergers are taking place, whether they're in the centers of galaxies or on the outskirts or even outside galaxies. So I think right now, empirically, we really don't have enough data on the black hole systems to say much about their kick velocity distributions. And the main reason for that is that the distances aren't good enough. So I hope that answered the question. If not, if there's a follow-up, I'd be happy to answer that.
I am not currently seeing any follow-up on that, so thank you. So we had a question about how LOFAR can be complementary to some of the NGVLA science you've been discussing. In particular, Alexandra was wondering if X-ray binaries that are seen at radio wavelengths, can be observed at LOFAR, and if that can add anything to the black hole mass estimation.
I would say LOFAR may be good at finding systems that have really anomalously bright radio emission, and it will almost certainly be good at understanding the physics of the jets of these systems. But I don't think LOFAR is going to be very helpful for understanding the system parameter stuff, just because it's much less sensitive and much worse angular resolution than even the VLA. So I think the way LOFAR ties in probably is different, I would say.
Do you know off the top of your head how the angular resolution of LOFAR compares with NGVLA?
Let me see. The highest frequency for LOFAR is about 200 megahertz. And the longest baselines, I think, are probably a factor 2 or 3 shorter. I'm not sure off the top of my head, but I think LOFAR can maybe get you down to arcsecond angular resolution, maybe a 1/10 of an arcsecond if you have the highest frequencies and the very longest baselines that they have. But it's so I think it's really more comparable to the current VLA for angular resolution.
Okay.
And I think you just can't, unless we get these low frequency antennas on the moon, I think you just can't have those low frequency wavelengths compete with higher frequencies in astrometry. Also for astrometry, the systematics tend to get much worse as you go to low frequency.
Yeah. I think we had a follow-up question. Can you say what the approximate distance limit for NGVLA parallax measurements will be?
That's going to be really systematic dependent. So I think the way to think about it is probably that the systematics on the positions are going to be limited to about 1 microarcsecond. And so if you have a source that's bright enough, you could go out to about 100 kiloparsecs. But then you're probably not going to have that many sources that are bright enough.
Yeah. All right. Thank you.
And that systematic will depend on having a fairly nearby phase calibrator also. But one of the advantages of the big sensitivity is that you can use fainter sources as phase calibrators, so you'll be more likely to have one nearby.
Yeah. While we're digging into the astrometry details, can you say a little bit about how the estimated astrometric precision for NGVLA will compare to the wobbles that you can expect in the best cases for the binaries you mentioned?
Yeah, so in the best cases with the current ones for SIGX1, I think it's about 50 milliarcseconds. That's off the top of my head. The best cases would be if we had something kind of like SIGX1 at a similar distance, but with a much wider separation. And I think that's quite realistic to expect, because if we did have something at a much wider separation, it would be much fainter in the X-rays and it may not have drawn attention to itself. And so I think it's quite reasonable that we could have objects that would have even almost a milliarcsecond of wobble. You know, we might need to be lucky with that, but I think another way to think about this too is that if you talk to the people who do binary evolution calculations for gravitational wave sources, they mostly think that objects like SIGX1 are too close together, so that probably that wouldn't lead to a gravitational wave source. Instead, it would lead to a merger before the second supernova happened. So based on the fact that we have gravitational wave sources, we kind of have to have the possibility of having binary systems with a black hole and a black hole progenitor that are much wider than SIGX1. How many of those we have and how close they are is, you know, maybe a matter of more debate, but I think it's reasonably likely that we'll have some good candidates out there.
Cool. So quite a few people are wondering, if you do not have an EM counterpart to a supermassive black hole merger, will you still be able to pinpoint the siren to a particular galaxy in the cluster in order to be able to combine it with the proper motion information?
Yes. Okay. So I want to actually step back on that and clarify a point that goes into the premise of the question too. It's actually the stellar mass black holes that you'd be looking at with LISA in the Virgo cluster. The rate of supermassive black hole mergers is probably small enough that we don't have a good chance of finding a merger that close. So instead what we get would be, say, 20 plus 20 black hole that's a long way away from merging, that's almost a continuous wave source, kind of like the stuff that LISA does for the white dwarf binaries in our own galaxy. All right, so now then the question is, how well will you be able to find the right galaxy that's associated with it? And that is the hard part of this issue. And so I think it would be a little bit of an iterative process. So we'd be able to get a standard siren distance that would be accurate to about 1%. And then you'd probably have to make some probabilistic arguments because the LISA positional accuracy is only about 1 degree. And there are likely to be multiple galaxies within a degree, but they're not likely to be multiple large galaxies within a degree. So it's probably going to be one of the large galaxies. Just because there's so much more stellar mass there, and there's especially so many more globular clusters there, and that's probably where these black holes originated. All right, so that's one thing that you'll do as part of the process, and then probably as we go forward, we'll have things like surface brightness fluctuation, distances, and techniques like that will get more accurate, so that you'll be kind of just refining the distance to the right galaxy. So you'll probably be able to filter out some of the potential companion galaxies using other distance techniques that are just not as good as the standard sirens. So that I think is the biggest concern with this technique, but I think it's a solvable problem.
Question asker says, thank you very much for the clarification.
Okay, thank you.
And sorry, Krista, when you said SMBH, you meant stellar mass black holes.
Oh, okay.
I don't know if she said SMBH. Yeah.
Okay.
So,
right, well, about that, I'm glad I clarified it.
Yes, thank you. So we have a pretty open question, which is, can the NGVLA help us place constraints on the formation of LIGO black hole mergers?
So I think that's I'd have to think about what is meant by that question. So I think we can place a lot of constraints on the evolutionary processes that lead to these systems. So if that's what you're asking, then definitely. If you're asking about whether the actual radio observations of black hole mergers would be something that we could study with NGVLA, I would say it would probably be worth looking at these systems just in case there's some electromagnetic signature, which might happen, for example, if the merger takes place in an AGN accretion disk or somewhere where there's some gas around, but I think that's pretty unlikely.
Yeah. I'm not sure what this person had particularly in mind. Do you want to say a little bit about what you think are interesting prospects for constraining the evolutionary scenarios that lead up to the black hole mergers?
Yeah, okay, yeah, sure, yeah. So in terms of the evolutionary scenarios, I think one thing is if we can go and find these wide black hole high mass binary systems, which I think we will be able to do with NGVLA, we can maybe able to actually see Milky Way versions of the progenitors of those systems. But the other thing is we can get just better understandings of the kick velocity distributions and mass distributions of black holes and binaries in a more general sense.
Thank you.
And I think actually, I would actually just add something. I think the SIGX-1 observations already are starting to tell us that the maximum masses that we can get for normal black hole stellar evolution are a little bit higher than what we had thought before those data were analyzed.
Okay. Yeah. I have a question here. I'm not sure what in particular it's referring to, but they say, can we assume that the hypervelocity stars are coming from a kicked star in a binary system with a black hole?
Okay, so yeah, so I think this isn't really directly related to my talk, but I know a little bit about this topic. So we have these hypervelocity stars that are moving, above the escape velocity from the Milky Way galaxy, and they almost certainly have to form through some kind of binary interaction process. Whether we start with a binary and have it come in and interact with a single black hole, like an active galactic nucleus black hole, I think that's the prevailing view for the most common way of having this happen. But you can also have some kind of case where you have a black hole binary and another star interacts with that binary. But it's really hard to do to make those systems without some kind of three-body interaction.
Yeah. Okay. Yeah, I'm not sure if there was more follow up on that. Sorry, just giving it a second to see if the person wants to respond, but I don't see anything. Right, and then there's some interest in this jet eclipse mapping question you had. The jet eclipse mapping project you mentioned. They're wondering what aspects you could model,
Mm-hmm. Okay,
including for example, if it's optically thin, if they're opening angles, jet speeds, etc.
Okay, so when I've done the calculations in the paper, and I'd be happy to send you a draft of the paper if you want to see it afterwards, just send me an email to remind me. But what I'm assuming is that you have an optically thick jet. If you have an optically thin jet, then the radio emission is probably coming from a very wide range of radii, and it's not really clear what you'd learn from doing the eclipses. If you're looking in the optically thick part of the jet, you could figure out where particular frequencies are coming from based on the duration of the eclipse. And by then going and doing that, you should be able to map out the structure of the jet and figure out different parts of the jet come from different places. Now, in terms of understanding the speeds of the jet, I think that actually is done better by techniques that go back to what I was kind of referring to that Alex Teterenko has been doing, that if you observe time delays for where the radio emission is coming from at different frequencies, then you can also map out the acceleration of the jet. So if you have both of those techniques working on the same system, then you can really do some powerful things. The other thing is, if you look at the eclipses at different luminosity levels, you can see how the structure of the jet changes as a function of the power put into the jet. All right, now, you also potentially might be able to do this to resolve the transverse part of the jet too, and see what the opening angles of the jets are in directly. That's something I think is going to be really hard, because the best guess is that the opening angles are only 1 or 2 degrees. So that'll make the jets typically smaller across than the size of the donor star. And if that's the case, it won't affect the eclipse profile very much. But if we look at really bright systems with NGVLA where we can get exquisite data and we repeatedly eclipse map them, then I think we have some hope of getting some information about the opening angles as well.
Okay. Yeah.
Yeah. Also, I guess because the amplitude of the eclipse will also tell you something about the speeds, because if the amplitude is only 10%, that tells you something about what the ratio of the counter jet flux to the approaching jet flux is too. So you do have that technique at getting at the jet speeds as well.
Okay. Hopefully that answered the other question about jet eclipses too, maybe? That's what they meant by periodicity?
Yeah, so so maybe I can answer that. Yeah, so maybe you can read the question to everyone. Or?
They're wondering, is there, in the jet eclipses, should there be any periodicity? And if so, can you use this to extract any physical parameters of the system?
So I'm going to say yes to that. And there's some systems that we've known for a long time that we don't even know what the orbital period is. And those tend to be systems that are persistently bright. And that is actually often makes it harder to get the orbital period from the optical donor star. Right. So that's another thing that you can do with these jet eclipses is that you can get the orbital periods for systems that are otherwise hard to measure. But something I maybe went through a little bit too fast is that the eclipse duration will be different depending on what the inclination angle and mass ratio of the system are. So you can get at some of the other system parameters as well.
Cool. Somebody mentions that LOFAR can definitely do sub-arc-second resolution. Just an FYI for anyone.
Yeah, I think what I said was probably about 0.1 arc seconds. It's definitely not going to get to milliarcsecond.
Yeah.
All
right, we have one more question, and then we'll wrap it up. So people are wondering, how can the NGVLA interface with the Event Horizon Telescope? And do you know any improvements that will be manifested for the HT through through NGVLA is the question. And then there was a question of, is there any overlap in frequency between the NGVLA and the HT?
I think for the actual event horizon, so the highest frequency for the NGVLA, I think is 110 gigahertz. That might be off by a few percent, but it's in that ballpark. And I think the lowest frequency for the EHT is higher than that. And so in terms of getting the maximum, I don't know if the dishes would support putting a 300 gigahertz receiver system on eventually. The other thing that you might think about is there might be some systems that you might like to observe at lower frequencies, and then NGVLA may be able to do something with them. I think you probably have to add some space antennas to get the resolution that you would really want. But space antenna technology is getting much better. Some of that is being driven by some things that are rather unfortunate for us, like satellite internet. But it may not be crazy in the future to have a 50-meter antenna in space that observes at the highest frequencies the NGVLA does, and that might then open up doing EHT-like science on some systems where you want to observe at lower frequency. But I think in terms of directly interfacing with the EHT, there's not so much there.
Tom, you're never afraid to dream big. I like it.
Sorry? I think this is something we should be thinking about seriously.
Yeah.
I mean, there's already a little bit of space VLBI going on. It just tends to be only for 10 Jansky level blazars.
That's very true. Yes. All right. So I think that's all we have time for now. Thank you so much for joining us. And thank you, Tom, for your lovely talk and your great ideas. And we'll see you in a couple weeks. Thank you all.